Yeah, we can hear you.
Okay, we are recording now. Um, First of all, um, the pre-notes. I've been posting the pre-notes for the class on the webpage. I know I'm doing it pretty late. Right now it's available, so feel free to download the pre-notes in case you would like to write on top of that. Um, that's basically just the black notes and then I write in red. Okay, so let's get going. One of my main big aims in life right now is to finish the class in 1 hour 20 minutes. Okay, I know many of you might be grinding your teeth for that. Um, I'll try to do that today. Today we are moving on from foundations to uh, applications. Basically, now we are going to apply some of the things that we are learning into various applications, and in the process also learn about those mobile computing applications. um, of course, everything that we've done is much more general, so not everything will get applied today, tomorrow, or even through the course. Many things would be useful even later and may not directly apply to everything in this course. But um, that foundation lectures that we had would serve as good background, would help you think about, reason about things in a bit more systematic way than many systems designers, engineers would do. Okay, so the next couple of lectures are all around localization, and we are going to start, and the high level motivation is that mobile devices today have a whole bunch of sensors on them, right? And these sensors include things like GPS, right? GPS is a radio, it's a wireless sensor in some sense, but it's still a sensor because it senses your location. So GPS, there are other sensors like IMUs, inertial measurement units, which contains accelerometers, gyroscopes, and magnetometers. There are sensors like your microphone, which senses sound. There are sensors like your cameras. There are light sensors, which actually senses the ambient light, which is used for understanding whether your phone is close to your ear or not. That is how your phone's screen lights up or dims out. Whenever you bring your phone close to your ears, the screen dims out by looking at the ambient light sensor and what is also called a proximity sensor. There's also a proximity sensor. Um, Certain phones also have, or mobile devices also have barometers, which measure pressure. There are temperature sensors, it seems, on some phones. Uh, Wi-Fi sometimes is also becoming a sensor because the Wi-Fi signals can be used like radars or sonars to actually understand certain things. We are going to look at some of that downstream in the course. Uh, the mobile phone also has a vibration motor that buzzes the phone. That is also kind of an actuator cum sensor, which is also becoming useful. Um, so there's a wide array of sensors, and we are going to touch upon some of these sensors throughout this course in the context of certain applications. Okay. So today we basically start on this journey, uh, and today's topic is basics of GPS. And feel free to jump in and ask questions as we move forward. And today we're not going to dive into GPS in any depth. It's just a superficial high level introduction. But then we will go into Wi-Fi based localization, which aligns more with the theme of the course, which is mobile devices, IoT devices, um, uh, wearable devices, those kind of devices. But GPS is kind of important to understand how things started and for coverage and completeness of the topics. Okay. Questions thus far? Okay. I hope you're working on your MP1 and homework too. Um, Once this MP gets submitted, the next MP will probably get released on Monday, which is the MP around Wi-Fi localization. Okay, great. So let's get started. So GPS, let's start with some trivia. Um, all of you pretty much know that there are multiple satellites that are roaming around, orbiting around the Earth. And these satellites essentially give you sense signals, and mobile phones or mobile devices, GPS devices on the Earth receive these signals, and then they actually figure out their own location from these satellite signals. So if you think about the orbits around the world, there are three kinds of orbits largely. One is called the LEO, which is the low Earth orbit. The next is MEO, which is the medium Earth orbit. And the farthest away one is called GEO, which is geostationary Earth orbit. Okay. So here is LEO, MEO, and GEO, the full forms. The geostationary Earth orbits are where when there's a satellite over here, and if the satellite is beaming onto some place on Earth, actually I should draw it better. Geostationary means that that satellite will stay on Chicago, for example, all the time. Okay? Stationary with respect to a point on the Earth. So roughly, if you think of the distances, LEO satellites are around 1,000 miles above. MEO is around 6,000 miles. And GEO, any guesses? Make a random guess.
15,000.
15,000, 22,000 miles actually. Okay, so these are basically the three main classes of orbits, and satellites for various different purposes are put on these three classes of orbits. Okay. Now, GPS, which is called Global Positioning System, is the name of a project that the US started in the 1970s and launched the satellites with the aim of actually giving localization to all points of Earth on Earth, but specifically targeted to points on the US. Okay, so this is just our USA's positioning system, but various other countries have their own positioning system. For instance, EU, the European satellite system, is called Galileo. Russia has its own, which is called GLONASS. And every country designs its own satellite systems. They have varying number of satellites going around the Earth. Their frequencies are different. Their technologies might be somewhat different, although the basic principles would be the same. Japan has what is called quasi-zenith. India has IRNSS, and China has Beidou. Okay, so these are the different satellite systems, and of course, all these satellite systems are going around this Earth, and some other countries might share satellite systems with systems that have already been launched into orbit. Okay, so GPS satellites, there are typically 32, not typically, there are 32 satellites that are going around the Earth. All around the Earth, they're orbiting, and they are mostly in MEO. Oops. Okay. Almost all of them are in MEO. I think there is one or two in GEO or low Earth, but for all practical purposes, you can say that GPS satellites are on MEO. So why were GPS satellites put onto MEO as opposed to LEO and GEO? Well, the reason is LEO is too close to the Earth. As a result, every satellite in LEO has a small footprint or coverage. Okay. And that means you need too many satellites to fully cover Earth. Okay. Clearly, right? If you have a satellite over here in LEO, the coverage is smaller. Now, then why not go to GEO? Because GEO would be far away. You would get a huge coverage. Why not go to GEO, guys?
Maybe some latency issues.
Latency issues could be an issue, but you do not care about latency, right? You only care about your location.
Then maybe resolution is too far. You might have less resolution.
Resolution. Why?
Because if one satellite is covering a big area, then you computationally you might not be able to cover more points on Earth.
I see. Actually, I see your line of thinking. That's good, but it may not actually affect resolution because you're not thinking. I mean, satellite cover. We are not going to solve the problem by Venn diagrams. It's like multiple satellites. Multiple satellites have these coverage areas, and oh, you are in this region. We will not solve it like that. If you solved it like that, then you would have coverage resolution issues. But we are going to solve in a different way that we call trilateration. But the main reason over here is the signal becomes very weak by the time it arrives on the face of Earth. Okay? And that is why GEO is not a good orbit for many applications, actually. Okay, great. So this is the reason satellite GPS picked MEO, and 32 satellites are going around the Earth in the MEO orbit. Okay, good. So now what these satellites essentially do is that they send constant beacons, okay, that are repeating signals saying, hey, I am so-and-so satellite, and this is my time. This is my timestamp, right? And they're constantly sending this. Okay? So the data that is coming from the satellites is actually at a meager 50 bits per second. Okay? That's really, really low. So the satellites are sending, hello, I am satellite number 574324. My clock timestamp is this, and my location is actually this. So it also sends the location. So 50 bits per second being sent continuously from the satellite. Why so low? Why such? I mean, you know, right? Today's Wi-Fi bit rate is easily around 30 to 50 Mbps, right? Mbps is 10 to the power 6. So in some sense, Wi-Fi bit rate, Wi-Fi speed, Wi-Fi data rate is 1,000,000 times higher than the satellite data rate, right? Wow, right? Why? Why can't the satellite send me more data? Well, again, it goes back to the same answer that these signals that are coming from the satellite are very weak. And whenever there is weak signal, the bit rate or data rate goes low. Okay. So very brief intuition for that is that imagine you have a signal versus imagine you have a strong signal over here versus you have a weak signal over here. Same sign signal, one is strong, one is weak. If the signal is strong, what you can say is, look, when you sample that signal, you can divide the amplitude, the y-axis, into fine values, fine resolution, and say, oh, if it is in this region, then I expect to see 0, 0, 0, 0. That means 0, 0, 0, 0. If the sample falls in this region, if the sample falls in this region, then it's 0, 0, 0, 1. If the sample falls in this region, then it's 0, 0, 1, 0, and so on. If you have 8 of them, you can go to, if the sample falls in the highest region, you have 1, 1, 1, 1. So each sample is giving you information for how many bits? How many bits, guys? Each sample? Every time you get a sample, how many bits of information are you getting?
4.
4 bits, right? So imagine I want to send a bit sequence which is 0, 0, 0, 1, 1, 1, 1, 1. These two samples, so my signal would look like a small sample and a big sample. Right? And I have conveyed all the 8 bits from just these two samples. But if the signal is weak, then you cannot, you do not have too much amplitude over here. Your amplitude is very low. You cannot divide this y-axis into fine-grained, right? So in this case, you might be only able to divide the y-axis into 2, and you say, look, it's either 0 or 1, right? So when you sample, it's either 0 or 1. So now if you want to send a signal which is 0, 0, 0, 1, 1, 1, 1, 1, you have to send 8 samples to convey the same amount of information. Does that make sense? Okay. So weaker the amplitude of the signal, you cannot chop it up into fine-grained buckets. The amplitude basically gets chopped up into buckets. And wherever, whenever, and whichever sample that, whichever bucket that samples falls into, that's what you receive as the value. And as a result of that, weak amplitude signals give you low data rate, high amplitude signals give you much stronger data rate. Again, there's a very, very high level intuitive understanding, but it should give you some sense as to why weak signals from GPS gives you such low data rates. Questions? Okay, very good. Okay, so GPS is a satellite sending 50 bits per second, and it's sending this continuously, back to back. Okay, and the data that the satellite's sending contains two important things. One is the clock, its own clock, the clock of the satellite, and what is called ephemeris, which is essentially the location of the satellite. Okay. So these are the two important pieces of information that the satellite is constantly broadcasting. And the GPS receiver's goal is to receive these signals from the satellites, from different satellites, and compute its own location. Okay. Now, one thing that's important is that for localization to work, all satellites need to be clock synchronized. Okay, and we'll see why, but let's take this for granted that satellites need to be clock synchronized. So then how do you synchronize the satellites? Okay, so that is a question that's an important question. And for this, what we have set up is what are called GPS control centers. And these GPS control centers are all across the world on the surface of the Earth. They're in Hawaii, Colorado, Atlantic Ocean, Indian Ocean, Pacific Ocean. They're all over the place. And these GPS centers are actually recording all these GPS signals constantly, ingesting them, computing the satellite locations and clocks, and then estimating how their clocks have drifted. Okay? And once they estimate how their clocks have drifted, then they upload the correct estimates. These corrected estimates are uploaded back to satellites to adjust their own clocks and their ephemeris and their locations. Okay. Remember, these satellites are in free fall, right? But even then, things change with minute amounts. And because we are dealing with signals that are traveling at the speed of light, we really want to be very precise about the clock and the location, because a small mistake will get magnified by the speed of light. And therefore, that will be very bad. So we really want to be very precise about the clock and ephemeris. And therefore, these GPS control centers are constantly doing computation, figuring out the precise ones, precise clocks and locations, and telling the satellites, this is your clock, this is your location. That's what you want to broadcast. Okay. In fact, infrequently, major readjustments are needed. Right? So typically the satellites the satellites have atomic clocks, which are very, very precise. They're very expensive clocks. So they're pretty much, they don't become desynchronized like our mobile phones do. So major adjustments are typically not needed, but every now and then major adjustments are needed. For instance, a satellite fails and it was covering a very important area, and now we need another satellite to cover for that area. Right? So sometimes a satellite will be moved, right? And they will actually have the jets to actually move the satellite. So, you see these in movies, right? You move the satellites, you turn it this way. All that happens infrequently, rarely, but you have the capability to move satellites and change their clocks completely so that they can take over another satellite, or maybe during war. So during failures or wars or kind of surveillance kind of scenarios, we might need to do these major adjustments. And GPS control centers control all of that, all of those adjustments.
Professor?
Yeah.
When you talk about synchronization, are they synchronized to like per GPS system, or all the GPS like satellites are synchronized?
All the satellites means not across countries. All US 32 GPS satellites, all these 32 GPS satellites would get synchronized to each other.
Okay.
Does it make sense? Was
Yep.
that your question?
Yeah.
Very good. By the way, just as a trivia, if relativity, Einstein's theory of relativity was not known, these GPS satellites, GPS-based localization wouldn't work. Okay, so actually satellites and the time compensation they do takes into account the general theory of relativity. Okay. We won't get into that, and I do not know too much around that too, but that was kind of an interesting thing that, to be able to launch satellites and do localization, you need to account for relative time shifts, time dilation, and use that in your algorithm. Otherwise, your localization would screw up. Okay, good. So basic idea with GPS localization. Okay. Idea is simple. Every satellite knows its own location. Let's say satellite 1 knows its location x1, y1, z1, and the superscript is S, meaning satellite. And the satellite is sending this location, that is its ephemeris, and its timestamp And the receiver receives that. And the idea is the receiver wants to compute the distance R1 to that satellite. Okay. The receiver also wants to compute distances R2, R3, R4 to multiple satellites. And the hope is if the receiver can get access to 3 satellites, can compute the distances from 3 satellites, then you can draw a circle of radius R1 around satellite 1, radius R2 around satellite 2, radius R3 around satellite 3. And if your measurements R1, R2, R3 are precise, then all those 3 circles should meet only at one point, and that one point should be the location of the receiver. Does that make sense? Right? If you have 2 circles, it will meet at 2 points. If you have 3 circles, it should meet only at one point if you know the location, if you know the distance from those circles. So this is the high level idea, right? But this is again very high level. We'll look at a little bit of the details, but let's basically write that algorithm in a pseudocode kind of a way, in a very high level language pseudocode. So receiver measures distance from itself to each satellite. Let's call to satellite I, let's call that satellite I. And this distance is called Ri. Now, the receiver formulates this as a AX equals B problem. Haha. Okay. Let's say that the receiver's location is X0, Y0, Z0, right? So X0, Y0, Z0 are really the 3 unknowns we are looking for, right? So I formulate this as a AX equals B problem, where X is X0, where this X unknown vector is X0, Y0, Z0. Okay.
Wait, Professor?
Yes.
So are the blue and the red satellites in orbit and the black one like us on Earth?
No. What do you mean?
Like, are we trying to compute like location right now, or what is this situation trying to accomplish?
Oh, okay. Sorry, maybe I confused you there itself. Let's say this is Earth. Let's say this is Earth. This is your mobile phone on Earth. This is one satellite. This is another satellite. This is another satellite. Okay. The distance from, let's say this is satellite number 1, 2, and 3. This distance is R1. This distance is R2. This distance is R3.
Okay.
Okay. Does that make sense? Now, can you
Yeah,
connect?
that makes sense.
Yeah. Now, can you? I hope you can connect this to this.
But then essentially X, Y, Z is from reference point. Where is that reference point from? Like the mobile center?
Yeah, there is a reference coordinate frame on which the ephemeris and the user's location would be computed. That is your GPS latitude, longitude.
Okay.
That reference frame is with respect to Earth.
So that black dot then is essentially that place that localizes everything?
This black dot is your phone's location, which is this location.
Okay.
Right? And at your phone's location, the R1 circle, the R2 circle,
Yeah.
and the R3 circle will intersect.
Okay, got it. And then you're saying we know what the XYZs are for the blue and red satellite?
We know the XYZs for all the satellites.
Okay.
Right? Because we launched the satellites, we know exactly how they're moving. And
then I'm trying to figure out X0, Y0, Z0. Okay.
Yeah. X0, Y0, Z0 is the only unknown. X1, Y1, Z1, and R1. R1 we need to measure, right? But X1, Y1, Z1, xi, yi, zi, I not equal to 0 are all known. X0,
Yeah,
Y0.
got it. And last question, why can't we just use two circles again? Why do we need
Why can't we use two circles? Because
like I can't picture why that would not work in my head.
Yeah, sure. If you use two circles, the two circles intersect at 2 points. So you'll have ambiguity. You will not know. I mean, imagine this satellite number 1 and 2, right? They may intersect like this.
Got it. Okay.
You may not know whether this guy is flying on a plane or this guy is on the other side in Asia.
Yeah.
Even though that guy is in Chicago. No, okay. Actually, sorry. I have to be careful. Let me draw this with blue. Let's say this blue circle is for satellite 3. How do I draw this? And let's say the satellite 3 is at the center of this blue circle. Okay. Does that make sense? Adil, is that Adil?
Yeah, no, that makes sense.
Anirudh, right?
Yeah.
And so now you do not know if the phone is over here or the phone is flying in a plane over here.
Mm-hmm.
Right? One of the points is the correct position.
Yeah.
Right? But you don't know which. So to resolve that, you need the third satellite, which will give you this circle.
Okay. And these are all in different trajectories?
What do you mean?
Like they're not going to be launched at the same altitude, right?
They are at very similar altitude, but they are all from the center of the Earth. From the center of the Earth, they are at equal altitudes.
Okay.
Why do you need 3 satellites and not 4?
Why do you need 4?
Because I'm assuming like it's not like a circle that's being sent up, but a sphere, right? So in that case, wouldn't you have like with 2 satellites, you would have an entire circle of collisions or possible locations you can be at. And then with 3 satellites, that would be down to 2.
Wait, you might be right. 2 spheres would intersect on a circle, and 3 spheres would intersect at 2 points, you're saying?
Yes.
Yeah, you're right. I think you're right. I think what they do is...
Well, could you repeat the question?
The question is that these are actually spheres around the satellite. So these 2 spheres, when they intersect, they form a circle. 3 spheres, when they intersect, they form 2 intersection points, the intersection of 2 circles. Okay. Okay. So first of all, Lucas says Google seems to agree that they need 4, but they need 4 for a different purpose that we'll talk about later. But Utkarsh, I think one of the reason is that given that you have to be on the surface of the Earth, and that's a 2D surface, once you put in that constraint, you don't need the third one.
So GPS can't localize if you're on a plane or something?
GPS can, because GPS actually ends up using 6 and more satellites, so they over-determine the system.
Okay, that makes sense then.
I mean, I think
So
that may
the-
be the case, but for the purposes of this class, I think we understand the point of how three circles get to, a single point, right?
Yeah, I assume that they just put the Earth as the fourth sphere, which helps narrow
Yeah.
down where you are.
Yeah. Because they know exactly the location of the Earth as well. Yes. Okay, good. Good questions. So AX equals B, and we now need to solve for X, which is really X0, Y0, Z0. Now, importantly, when you receive a signal or when you are measuring this distance R1, R2, R3, if your measurement is not absolutely accurate, can someone tells me what happens to AX equals B? Okay, what is this B? This B will turn out to be the measurements that you make, right? So now when the measurements of R1, R2, R3 are not going to be absolutely accurate, then it'll turn out that B does not fall in the column space of A. Thus, you need to solve least squares. Haha, right? I think we just mentioned this when we were doing least squares, right? So you want to solve for B. B does not fall in the column space of A. So you might as well solve the best possible projection and say that's the best estimate location that you have.
Professor, I thought we had enough satellites to not have to do least squares. Sometimes it's not in the column space of A, sometimes there's not enough satellites.
Lucas, let me think how to quickly say this best. Imagine a thin matrix A. Let's say this is 10 cross 3. Okay.
Yeah.
And then you have X0, Y0, Z0 equals B. B is 10 cross 1. Right?
Okay, yeah.
If this is our AX equals B formulation, how many satellites are there?
3.
Hey.
Or 1, I guess. 1, right?
What are the elements of B?
It's like measurements from, oh, so that's like 10 satellites.
Exactly. So this formulation, if I give you and say the GPS problem, the GPS chip in your phone is solving this AX equals B problem, how many satellites is your phone seeing? You should be able to say, my satellite is seeing 10 phones. Agree?
Yes.
Sorry, my satellite.
Yeah, other way.
Yeah.
Yeah.
My phone is seeing 10 satellites. Okay.
Mhm.
Hey, now tell me, how many solutions are possible for X0, Y0, Z0?
Shouldn't it just be just 1? Just 1.
Okay. Anyone else? 10-dimensional vector in 10-dimensional space, right? There's a 3-dimensional vector.
Oh, no solutions.
Why?
There's no way you could reach 10 dimensions with a 3-dimensional vector, right?
Wait, why? This is going to be x0 times a1 plus y0 times a2, where this is a1, this is a2, this is a3, plus z0 times a3. Right? This is a 10-dimensional vector, right? Lucas,
Yes, yes, I follow. Yes,
right? Right?
yes.
So this should be a 10-dimensional vector. And all these, as long as these three columns are linearly independent, can I say I'll be able to form B?
Yes, right. Oh,
Someone else, everyone. This is back into our basics of linear algebra.
Okay, but a 10 by 3 matrix multiplied by 3 by 1 should give a 10 by 1 matrix, right?
That's true. But can I say true or false? This will surely have a solution in this case.
I mean, that's only if they're on the same, what's that term again? They're on the same,
column space of A, right?
Hmm?
what's that term where they have to like they have to lie on the same plane? That's not singular, is it?
Same basis.
Yeah, or something like that. I mean, I don't know exactly what the term is called again.
This would either have like infinitely solutions or no solution or one solution, right?
Wait, isn't that like the entire?
I mean, isn't it 0 or 1 solutions? 0 solutions if B lies in the column space of A1A and 0 if it doesn't.
That's it.
So why wouldn't we be in the column space of A though? That's the part.
Again, let's go back to our pens. Each of these pens are 10-dimensional vectors, right? 10-dimensional vectors. And there are only 3 of them, right? So what space do they span?
R3.
R3, right? But imagine this black vector, which is also 10-dimensional, but it's orthogonal to this R3, right? How many such orthogonal black vectors can you find?
Infinitely many, I think, right? Or no?
Okay, how many orthogonal, mutually orthogonal?
Oh, just one maybe?
Why?
7.
7.
Oh, well,
Because it's 10-dimensional space, right? So there are 7 such mutually orthogonal black vectors that you can find. So there's a huge space, 7-dimensional space that is not covered, even though each of these pencils are 10-dimensional vectors, right? There are only 3 pencils, right?
Oh, okay. Yeah, I mean, that makes sense. I guess we should probably like move on, but I was just confused on like why, like, but intuitively our space is not 10-dimensional. So if you have, 3 vectors in our 3D world, I would think that they could cover all space, but I mean, I get the math behind it. That makes sense. Like it's not in the column space of A.
What is not in the column space of A?
Well, I get why you're saying now, like with the 10 dimensions and like covering R3, you might have like places that X, Y, Z could be that isn't covered by the column space of A. But I'm just like, I guess like the weird thing to me is like, why is the column space of A like I don't know, intuitively you'd think that in our 3D world that, as long as you cover 3 dimensions, you're good. But I get the math behind it, that helps.
No, okay, so Lucas, and for everyone, right? This B may or may not fall in this R3, right? May not fall in, it may fall in this R3. If it does, then we have a solution. If it doesn't, then we don't have a solution. So it's either 0 or 1 solution. Okay. And your original question was, we have 3 satellites. Why can't we solve the problem? Why do we need least square? Oh, even if there are hundreds of satellites, we might still need it.
Okay, thanks for
there are 10 satellites here, right? Right? But still we need it because the measurements are not precise. The measurements have error. Right? If the measurements did not have error, that means if measurements didn't have error, that means B would have fallen in the column space of A. But if measurements have error, B can be any vector in that 10-dimensional space. And therefore, you need least squares to solve it.
I see. That helps. Thank you.
Right. So oftentimes, remember, when you have many, so this is a case where there are many equations, many more equations than the number of unknowns. Right? This is often called an overdetermined system. More equations than the number of unknowns. But even if you have more equations than the number of unknowns, if the measurements, if the measurements don't satisfy, you may not be able to immediately solve it. You have to do least squares. Okay, good. So now GPS would solve least squares. And in addition to that, GPS receiver's clock also gets synchronized to satellite. Okay. This is an additional benefit that will happen. And this is why many places, manufacturing plants, electricity grid, etc., they all have GPS receiver, GPS chipsets in them, not because they care about the motion, the electricity grid is not moving, but they care about syncing with the GPS clock. Okay. GPS also synchronizes your clock. Very good. Now let's dive a little bit into how this is done. So this is a satellite sending a signal sending a signal with a timestamp of TS, saying this is my clock time. And the receiver receives that signal at TR. Okay. So now when the signal arrives at the receiver locks onto that signal and says, oh, I received the signal at TR. And by decoding the bits, the receiver says that the satellite sent the signal at TS. So then what can I say about the distance? R1 equals what? From this TR and TS, what can we say?
TR minus TS divided by the speed of light.
TR minus TS divided. Is that divided?
Multiply.
Right? This should give me the distance to the satellite. Right? Very good. So let's do that. So range R is TR minus TS multiplied by the speed of the sound. Okay. Now, this range is nothing but, if I want to write the distance from the satellite, is nothing but x1 s minus x0 whole squared plus y1 s minus y0 squared Do you agree? Right? This is the range, right? I've expressed this range as a function of known parameters and my unknown parameters. All of you with me? Guys, if you can turn on some videos, that will be great. If not,
are we saying that TR is known in this scenario?
Say that again.
Are we saying that TR is known in this scenario?
Oh, TR is your GPS receiver received the GPS signal and clocked it.
Mm-hmm.
So I know what time the signal arrived.
How do we know that that clocking is accurate? Like it's synchronized enough to get it to a high level of accuracy?
We will worry about that soon. But for now, let's assume you received a signal at some time and you compute your range from distance from that time. Right? You assume that you're synchronized to the GPS. Okay. Now, this gives you how many equations? This gives you only one equation, right? But how many unknowns do you have? You have 3 unknowns, right? So you need at least 3 equations, right? Very good. So what do? You need more equations. You do the same with other satellites. So you take your first equation as is, but you also compute it from x2s, y2s, z2s, x3s, y3s, z3s. You get these 3 equations, and now you're in business. You have at least 3 equations, right? 3 equations, 3 unknowns. Hey, but there is still an issue though. These are nonlinear equations. Do you agree? This is not a linear equation. These are nonlinear equations, but it's possible to linearize them. You can basically make this equation into some function of x1s, y1s, z1s times x0, or times x0, y0, z0. And you can make this a linear function. There's a way of doing it. I'll point you to a video, a very nice explanation on how you linearize those equations. And this is often done. So then once you linearize this equation, what do you have? You have now the ax equals b form, which is the following. So this is the linearized. Make sense? And how did you get this? This is your TR1 minus TS1 times C. C equals speed of light. So far, all right? Right, so you know all of these from all of the, you know these R's from the 3 satellites, you know the geometry, the locations of the satellites, the ephemeris, and x0, y0, z0 is your unknown. So now you've brought this down to this ax equals b form. And this matrix is called the satellite geometry matrix.
Hey, Professor, those equations up there, could you scroll up real quick? So how come you so you just did you not multiply by C just for like notation's sake, or is it supposed to be there?
Sorry, my bad. Thank you. You're right. Okay. So let's just do that for consistency. Yes, thanks, Anirudh. Yeah. So now you have the satellite geometry matrix, which is known. This is known because this is a function of the ephemeris. XYZ or X0, Y0, Z0, R1, R2, R3 is measured. If you solve this, you will get an answer. But that answer will give you 300 kilometers of error. 300 kilometers.
I thought you said the clocks were synchronized in GPS.
Say that again.
I thought you said the clocks were synchronized in GPS.
Clocks are synchronized across the satellites. The problem over here is your phone's clock and the satellite's clock, they are not synchronized, right? Across the satellites, these clocks are synchronized because GPS centers are telling all the satellites what their clocks should be. Okay.
What's the problem with using like a network time protocol with every?
Oh, tons of problems, because the kind of accuracy that you want is far stronger than what NTP would allow you to do. Okay. Also, one thing to remember is in many network time protocols, by the way, guys, network time protocols are what's used in the internet to synchronize devices. But in many network time or many clock synchronization protocols, what you do things like you send a message, the receiver responds back with a message, and the transmitter looks at the two messages, its own sending time, its own receiving time, and computes the clock delta. But what this assumes is that the receiver, by the way, this is time downward. This NTP or these clock synchronization protocols assumes that the receiver can send back messages to the transmitter. That is difficult with your mobile phone because you don't want all mobile phones to now send back information back to the satellite. You want this to be a one-way system where the satellite beacons, you receive and you figure out your location. You don't have any two-way chatter with the satellite. If you did that, your mobile phone's battery would drain dramatically because you have to send a signal all the way to the satellite. Make sense, Adil?
So, do the satellites get told the time to them by a different system, like a different?
That is only by these GPS control centers.
Okay.
Which are like, there are like central offices, maybe six offices across the world, which are special devices which can send signals with high power, beamforming, etc.
And that's the reason why mobile phones don't get these signals for like time?
That's the reason why mobile phones cannot connect to the satellite.
No, I mean, like, what if the mobile phones got the same timestamp from like the GPS centers?
Oh, that means these GPS centers would have to broadcast the timestamp to everyone.
Is that bad?
Oh, because...
Okay. Oh, yeah, I guess that kind of makes sense.
Right, yeah. The mobile centers are on the Earth, and now you do not know if the signals are not going to come in a straight line, they're going to bounce all around, and by the time you come, you have all kinds of other problems to solve for clock synchronization with the GPS centers. Right? Instead, you make a cheap device, which is just a receiver. It only receives signals and computes. It does not send back anything for clock synchronization. Okay, good. So 300 kilometers of error because of unsynchronized clock, simply because this clock at this GPS receiver and the satellite clock, they are not synchronized. What can you do? What can you do, guys? How can you solve this? And I want to put on your linear algebra hat and unknowns kind of hat and try to solve this problem. You have a clock synchronization error with a satellite. How can you solve this?
Find the error.
Okay, how?
At least squares or something. I don't know, apply it to this somehow.
Okay. So good. Utkarsh, I think you have an answer.
You're equally unsynchronized with every satellite, I think.
Correct.
So I think you can add a constant or something. I'm not sure.
Correct. Okay. So this is where I want you to think about things always as, what do I want? Or what do I not know? I do not know clock synchronization. Very good. how many variables do I need to model what I do not know? Right? In this case, you have 3 satellites. How many variables do you need to model what you do not know? Well, I have one variable for one satellite, one variable for another satellite, one variable for another satellite. But no, the satellites are synchronized. So if I can synchronize myself to one satellite, I'm synchronized with all satellites. So I really have one unknown variable, right? This is the kind of thinking you want to get into. Anytime you're faced with, I don't know how to solve this, ask yourself, how many variables do I not know? Right? Okay. So to solve all this 300-kilometer problem, there's only one unknown that you need to add to your X vector, which is X0, Y0, Z0. And that is delta T. Okay. I have one more unknown, but I have 4 unknowns. I have 3 equations. Where do I get the 4th equation? Anyone?
A 4th satellite?
What satellite? Right? I am now going to use 4 satellites, 4 unknowns. I'm going to solve it exactly the same way. Just that in my new formulation, I would still have A, which is 4 satellites, and I would have this new X vector, which is X0, Y0, Z0, and delta T. And that will be my 4 measurements, B1, B2, B3, B4. Okay. So now I write this as my range R is nothing but whatever my clock is, doesn't matter. I have only one unknown variable that I need to model. So this is my current clock minus the satellite clock times C plus some clock offset. Right? This is my offset with my satellite, my clock offset times C. Right? And I need to basically figure out what this clock offset is. If I'm ahead of the satellite, the clock offset will be negative. If I'm behind the satellite, the clock offset will be positive. Think about that.
So this is the reason they use 4?
This is the reason they use 4.
Ah.
Okay, very good. So now you have this satellite geometry matrix, right? Remember, you have 4 unknowns.
Hey, Professor, won't this be different for every single mobile phone? So wouldn't it have to be computed for each
Say that again.
For all GPSs, I mean, or all anything that uses kind of like something like that, then wouldn't that clock be specific for each device?
Yeah, the clock is specific for each device.
Yeah.
But
no, I mean like the error.
Hmm?
Like the error between the satellites and each device.
You mean this? You mean
device?
This error? This error?
Yeah. Mm-hmm.
Yeah, but this error is per phone, right? Per GPS receiver.
Yeah. That's what I was curious about. That's all I was asking.
Yeah, but that phone is going to compute its own error, right?
Yeah. No, that's fine. I just wanted to make sure.
Correct. Yeah. Okay. So you have the satellite geometry matrix, and you need to add C because delta clock times C is getting added to this. Okay, you need to look at this equation carefully. This part is what got added to your measurement, but you do not know this part. So you basically model it into your unknowns. So you have this range minus delta clock C. So this range minus delta clock C, this is the delta clock times C. I want you to think about this. This is trivial, but I want, if this is bugging you, I want you to go back and think about this. And this gives you your AX equals B formulation. Of course, your range that you have measured may not be right, may not be precise still, because the sample, when exactly the signal arrived, like Utkarsh was saying, when the satellite signal arrived at your GPS receiver, you may not know exactly what time it arrived. Okay, so there is still some noise over here. But even with that, even if you do 4 satellites with the clock error modeled, your error comes down to 1 to 3 meters.
Can I ask a question real quick?
Sure.
What is N1 to N4 here?
Oh, this is just a noise.
Oh,
When you receive the signal, there will be noise that will get added. That means your measurement has noise in it. Make sense?
Professor, I know you have R4 here, but in reality, shouldn't that R4 be like the variable that gets added to R1, R2, and R3?
This R4?
Yeah,
This
because
R4 is the measurement from the 4th satellite.
yeah, but I thought that's not, is that not used to calculate the error?
No, see, this is where you have to always go back to this AX equals B formulation, right? You have 4 unknowns, right? So immediately you can write 4 unknowns, X0, Y0, Z0, delta, right?
Mm-hmm.
This is your 4 unknowns.
Yeah.
You have 4 equations from 4 satellites.
Mm-hmm.
And what are those 4 measurements? B1, B2, B3, B4. Or sorry. Let's call it R1. Keep it.
Or R1, yeah. Now I know R1 is like the time difference between.
Yeah,
These-
R1 is your measurement,
Yeah.
right? So now you cannot, now this R1 is just your local clock minus what the satellite told you multiplied by C. You do not know this part,
Yeah.
right? You do not know this part. So you have modeled this part over on the left-hand side. You model this
Okay.
part in the left-hand side. So how do you do that? You take that same satellite geometry matrix for 4 satellite geometry matrix for 4 satellites, and then you add C over here. So now look what happens. This times this matrix, this times this matrix, plus delta times C gives you this. Oh, shoot. Hey, this is easy, but look at it once you go back home. See how you are modeling the system so that all
Yeah.
the unknowns come into your X vector.
So wait, you're saying that the satellite geometry matrix for 4 satellites is only being put into X, Y, and Z only?
No, this is like what? 4 rows, right?
Yeah, that's fine. I know there's 4 things, and yeah. Okay.
Right? There are 4 rows here, and you multiply this, and there are 3 columns. This satellite geometry matrix is a 4 cross 3 matrix. Okay. And
Yeah, no, I get it. And then we use that for X, Y, Z.
Now it's 4 cross.
I just never seen the notation before. You have like a whole column of C, and then you just have a clock, and that's added to everything.
Correct. Now the delta clock is getting multiplied to C. Is that clear, Anirudh? Hello? Hey guys, did we freeze? Hello? Hello? Hey guys, that just froze.
Yeah, I think the internet connection went out on your side.
Ooh.
Yeah.
You know what is the bigger problem with that?
Your
Is the recording messed up now?
The recording it did not record.
Oof.
it still says recording at the top left though.
Okay, we'll see what happened, but
You know, I think it'll be fine once this ends. You can still come But because even when you left, it still said
Hopefully
recording
they
the whole
have-
time.
We'll see how good Zoom is. Yeah, today I think we'll see how good Zoom is.
Yeah,
But
I think
this
it'll be
also
fine.
makes me think that maybe from now on, every 20 minutes, I'll just stop the recording and start again, because so that Zoom can create multiple recordings.
Yeah, okay.
Or maybe this is the advantage of coming to class. There is some
Yeah.
slight advantage of coming to class.
So, so quick question, Professor. So
Yeah.
you're saying here that so the satellite geometry matrix will be multiplied for X, Y, and Z. I get that format. It'll give us R1, R2, R3, and R4. But then how can you add another column? And then like, how does that,
You mean this column?
yeah. So then that column just gets added with the, multiplied with the clock. And that gets added to R1, R2, R3, and R4.
No, it's not getting added to R1, right? This is the total. Okay, look at this. This is your R1, R2, R3, R4, right? For every satellite.
Yeah.
So you bring this one over here. Make sense? Wait, look. Range minus delta clock times C equals TR minus TS times C. Agreed?
Yeah.
This is for one satellite. Right?
I get that.
Now this range, I can write this as f of x1s, y1s, z1s. Make sense?
Yeah. No, I mean, I get that the satellite geometry. I'm just don't understand how you're adding in the C and the clock. Like, I'm not getting that math.
Oh,
But I don't think we've done that in the homework or the class yet.
I'm not doing anything special. All I'm doing is x times this column plus y times this column plus z times this column plus delta clock times this column. Okay, Anirudh, let's do this off. Let's do this.
Yeah,
right
we'll do
after
this
class.
after class.
Let's do
Yeah,
this
that's
right
fine.
after. Yeah. Okay, good. So this gives you 1 to 3 meters of error. Very good. And as a result, because you figured out delta clock, you know what your clock synchronization is. So you have now synchronized with the GPS satellite clock, which is what lots of factories, plants, different instruments do. Now the question is, why do you even get 1 to 3 meters of error? Why can't you make it precise, millimeter, micrometer, right? And that has many reasons. Well, you know, in reality, the signal does not come to your receiver like in a straight line. So knowing this TR is not easy, because the signal is often bouncing off some building over here. Signal is bouncing off the floor over here, and all these signals are adding up from the GPS satellite. So among all these added up signal, you have to figure out exactly when did the signal arrive at my receiver. Does that make sense? This is not easy. It's like someone going to a valley surrounded by mountains and saying hello. And you hear this hello, 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 right? All these echoes are all overlapping on each other, and you have to figure out exactly at what time did that hello first start or first impinge at your ears. If you make small mistakes because you're multiplying things with C, that mistake will get heavily amplified. Make sense? So then the question becomes estimating the receive time TR at the GPS hardware. This is an important question, right? If this was a line of sight signal, only one signal coming to you, then it's no problem. I get 0, 0, 0, 0, 0, and suddenly I see the signal. But because there is noise in my hardware, if there's no signal coming and you ask your hardware, what signal do you see? Your GPS receiver will give you some value like this. So there is noise, right? And then when the signal comes in, suppose the signal is a sine wave, that sine wave and the noise will get added up and you'll get this signal. And now, given that you're receiving this black signal, you have to say, suppose the satellite is sending the red signal. You have to say, did the red signal start here? Or did the red signal start here? Or did it start here? And you have to be super precise, because even if you're off by 1 nanosecond, you'll be off by 30 meters. Right? Because you're multiplying it with the speed of light. So here is the question. Given that you have received this noisy signal, can you figure out exactly when the signal arrived? Actually, first question is, can you say even if the signal is there? In fact, interestingly, Alexa also does this. This is similar to decoding Alexa in speech signals. Okay. What is your Alexa doing? It's constantly listening and it's looking, is this Alexa word embedded in the speech signal or not? If it is, it wakes up. Right? So GPS has a stronger constraint, or has a stronger requirement, which is I need to detect if the satellite signal is there, or if this particular satellite is now within my reach, can I hear from it, which is like detecting Alexa. So imagine one satellite saying Alexa, another satellite saying Siri, another satellite saying Cortana, and your job is to figure out which satellite am I hearing. So this is that the detection is the same problem, but the GPS also needs to figure out exactly what time did the signal arrive, which our Amazon Echo and our Siri devices don't have to do. They don't care about exactly that time. They just care about the presence, the detection of that word. Okay, very good. So with that, we can ask this question in the following way. Let's say we are receiving a signal which is denoted as, you turn on your GPS receiver and you're getting Y5, Y6, Y7, Y8, Y9. These are the samples that you're getting from the satellite. And you know, you're looking for, maybe first you're looking for satellite number 1, and satellite number 1 should be sending you S1, S2, S3, S4, S5. Maybe we should just even add 1 on the superscript so that it says this is from satellite 1. Okay. Satellite 2 would be sending S1, S2, S3, S4, S5, but from 2. Okay. So your goal is to look for this signal, satellite 1 signal inside this, which is the same as your Alexa, your Amazon Echo getting some signal and looking for the word Alexa. Let's say Alexa signal looks like that, looking for this signal in the received acoustic signal. It's the same problem. And whenever you have to look for some pattern in another signal, any ideas on what you do?
Seems like it's NumPy. I use like NumPy correlation to do that.
Exactly, right? You basically get into you think of correlation. What is correlation in a very high level English language? Correlation means, okay, can someone tell me what at a high level, at a 10th grade level, what does correlation mean in English?
To like match two things and see how similar they're.
Good. Can you make it even simpler? What is match? When do you say two signals are matching?
When they look alike.
Can you define more clear? Can you define even more quantitatively what look-alike would mean? Suppose I say, give a mathematical definition of look-alike.
Maybe when one moves up, the other one moves up, and vice versa.
Perfect, perfect. Means whether two signals move up or down similarly. Why is this mathematical? Well, you take the product of two signals. If they move up together, means positive, their product will be positive. If they move down together, they both are negative, their product will be positive. So if they move up and move down together, their products are likely to be more positive. But if one moves up, the other moves down, their products are likely to be negative. So correlation is a simple idea. If I want to see similarity, just multiply the two signals. Right? Of course, you multiply the two signals first by making it zero mean. Right? You basically move it down and you make the zero at its mean so that the signal is oscillating around zero. Right? I hope you see this. If I take one signal like that and
I think his
another
internet
signal
cut
like
out
this.
again.
Sorry?
Big rip. Still recording though.
It broke again.
Does anybody hear?
Can you hear me? Ooh, can you hear me, guys?